Hello everyone. In this video we're going to take another look at the pencil production problem. So in previous videos we went through the problem statement that you can see on the screen now and basically worked our way from this problem statement to a mathematical model which represents the goals of it, which is in this case to maximize profit and not violate any of the constraints, which had to deal with the capacity in terms of inventory as well as the capacity in terms of the amount of labor. And so in that video, we worked our way to a mathematical model that looks something about like this, where x sub b was the quantity of the economy writer pencils to produce, and x sub d represented the quantity of the deluxe writer pencils to produce. And it looks like about the first four of these constraints that I have listed had to do with department level labor capacities, and then the remaining constraints had to do with the capacity in inventory of each one of the raw materials. And so you say, well, that's great, Brock, but it'd be nice to actually solve this and come up with the optimal value for x sub b and x sub d. And this problem's a little bit special in the sense that there are only two decision variables, right? X sub b and x sub d. And so what that does is allow you to use a graphical approach to solve it. And that's what we'll look at in this video. And so this isn't done a lot as far as in practice, so to speak, but it's a great teaching tool for individuals that are just starting off with linear programming, and so they can kind of see the idea of the feasible region becoming some sort of polygon and the fact that the optimal solution is going to be one of the vertices of the polygon. So with that being said, let's go ahead and hop right into this. I'm going to be doing a mix of work between kind of my scratch pad that I've got here, where I went ahead and recreated the model, and also my Jupyter notebook here. And so the first thing that's worth talking about is how we'll construct this graphical representation of this model. And so I'll come over here, and we'll be working off of a Cartesian coordinate system. So if you allow me to start sketching the green here, think of us having a nice Cartesian coordinate system. Imagine these are straight lines where let's call the bottom axis x sub e and the top axis x sub d there. So we're plotting the number of economy writer pencils on the horizontal and the number of deluxe writer pencils on the vertical. And so that if we just pick a point here in space, that point would represent a certain production plan, right? A certain amount of economy writer pencils and a certain amount of deluxe writer pencils. And there should be a way to develop a polygon in this case, since we're all going to have straight lines. Every one of these constraints is linear, so they'll form an edge of that polygon such that we'll have some sort of shape. We'll say it looks like that just for talking, that all the points inside of that shape satisfy all of these constraints. That'll be our first step, and then it's just a matter of finding a nice way to investigate the points associated with that polygon. So, in rough speaking, that it will be the plan. Let's remove all this. In actuality, our shape will be tied to the origins, because we know one possible plan is that right there, right? Not producing anything will satisfy all these constraints. It won't have any profit, but it'll still be a feasible solution. And so the way we'll do this is we'll start it by looking at one constraint at a time. So the first constraint I'll look at is this guy right here. And so I'll rewrite it down here. We've got 2 over 3600 x sub b plus 2 over 3600 x sub d must be less than or equal to 12. And the first thing I'm going to do is I'm not going to think of the inequality, but instead I'll just think of, well, what if that is an equality instead? And I would want to know things like, what is the intercept on this axis? So we could do that fairly straightforward. We could say let x sub d equal 0, right? That would allow us to find this horizontal axis. And if we do that, then the equation becomes 2 over 3600 x sub e would be equal to 12, and I could solve for x sub e. Just getting over to my notebook to do a little bit of scratch work here, I suppose. That'd be 12 times 3600 divided by 2. 21,600. Alright, so just talking about this constraint, I know there's a point somewhere out here, 21,600, and then it would also be nice to know this line in terms of kind of like a y equals mx plus b style of format, so I can isolate x sub d. So then, kind of the second step to this would be to isolate x sub d, and I would write that as x sub d is equal to 12 minus 2 over 3600 times x sub e, and all of that multiplied by 3600 over 2. And with these two pieces of information, I have enough that I can actually go into my Jupyter notebook and come up with a plot of this inequality. And the way I know that is I'm going to basically create a NumPy array that will go from 0, because we said the origin was in this feasible solution, and I'm going to have it march all the way across to this intercept, that 21,600, and I'll call that x sub e, and that will represent the array itself, and then I will be able to plug that x sub e into this relationship I've found for x sub d. And so let's go over to the Jupyter notebook and actually implement that. So the Jupyter notebook, I've already ran the first part, so I've imported the associated libraries. This is NumPy, and all this is kind of boilerplate code, you would say, for running the Plotly graphing library inside of the Jupyter notebook. If you haven't heard of Plotly, I'll give them a quick shout out. They make a great set of tools for doing analytical activities inside of Python. So at the base level, you could say, is this Plotly open source graphing library that I'll be using today. But you should also check out their website. Their kind of layer on top of this is what they call Dash, which is a nice framework and Python package for you to build these analytical web-based interactive dashboards, and you don't have to focus so much on the HTML and the CSS and the JavaScript there, but a lot of this stuff can be done inside of Python itself, and their tooling basically goes from taking your Python code and converting it into the appropriate HTML, CSS, and JavaScript. It's a very slick tool that I definitely use and appreciate. Alright, so with that being said, we're trying to figure out the feasible region. So I'll just give us a little mark here. And this constraint that we talked about, top level constraint, I believe has to do with the pre-processing. So I'll just make a function that is called pre-processing underscore trace. And what did we say? We were going to create a NumPy array. I'm going to use a range to do that. And we were going to go from 0 to the maximum value, which was 21,600. And I'm going to introduce a step size here. I'll just say the step is 1. And then we'll write that formula for x sub d that we just developed over here. 12 minus 2 over 3600 times x sub b times 3600 over 2. And then we will create a graph object scatter object. So this is the actual scatter trace, if you will. Setting the x and y arrays. Just giving it a name that'll show up in the legend. And let's just stop there for now. I'm going to come here because I'm going to have a bunch of these traces. So I'll call the function here inside of a list, so that'll create that in the list. And then let's just create our figure. So data now be traces. and we'll just do an eye plot here to show it at first. Okay, so that is the line. Let's do a little bit of cleanup here by creating a layout. And the layout will allow us to do things like set the x-axis title, for instance. It's called the quantity of economy rider pencils. And then similarly, we'll have a y-axis title. That'll be the quantity of deluxe rider pencils. And we'll also have a title for us. And the title can be Constraint Boundaries for this one. And let's blow it up a little bit. So it's all looking good. Just a little bit more. There we go. So this is the line. And so that would be the case if we treated this as an equality, but really it's an inequality. And so we need to find a way to test which side of this line satisfies that inequality. And in this case, the line doesn't go through the origin, so I love picking the origin to test with, because if I plug in the origin in here, x of b would go to 0, x of d would go to 0, and so it'd be 0 on the left-hand side. That is definitely less than or equal to 12, so I know that satisfies it. So really the points that satisfy that inequality are down here and to the left. And so the easiest way to show that with the processing tooling is to set the fill to 20y, and notice it will come down and fill this side of the Cartesian plane. And so that's great. This is all the feasible points, or all the points that satisfy the pre-processing requirement. So basically I can create any combination of these economy pencils and deluxe rider pencils, and I will not overburden that pre-processing department. Okay, the next step would be to repeat that same process for all the other constraints, where we would come up with, in a lot of the cases, the line associated with the inequality, then test the inequality, plot it, and so forth. Now, obviously that could become quite tedious, and so what I will do is shortcut that a little bit by just copying and pasting. I've went ahead and created all these functions before, so I will just take them, add them to this cell, and then we should just be able to go back and one at a time add them to this list. So just do the first one to check. Yep. And now notice the legend will start appearing over here. So if you'll give me one moment to do a little bit of copy paste work. We did the curing. Now we need to do the shaping. Each time we need to be sure to call the function itself to return that graph object. There's assembly, cedar trace, just peeking there. The last one was glue, was the next one we were going to see. Basic lead, then smooth lead. Matte paint, and then wood stain. Ferrule, eraser, and grip then. Alright, with any luck, we shall now have a number of traces on here. There we go. And so we end up with something like this. Again, we have a trace on here for every department and every part. And so the next question is, okay, now I've showing the boundaries and the feasible regions for every constraint. Really, we need to layer these on top of each other and figure out the common intersection amongst all of them. And so probably the easiest way to do that is to start going from the bigger constraints at the bottom. So you say things like, okay, here's the cedar blanks. Obviously, there's a region that's common that's underneath that. So essentially, this will not be a binding constraint for us. So I'll just toggle it off. Oh, cedar blanks. Hit the wrong one. There we go. Next step, it looks like the grip also would be the same argument. The eraser. The preprocessing, the first one we made there. Looks like it. I'm going to go ahead and zoom in on this little area here. Looks like the basic lead can go away. The glue can also go away. This blue here, I can see an area underneath it, so the ferrule can go. Smooth lead can go. Wood stain can go. Now we're getting down to the end here. It looks like the curing can also go as well. Alright, so I end up with what's active: the shaping, the assembly, and the matte paint here. So really our feasible region is basically starting here at the origin, goes up to this point here, which is the intercept associated with the shaping, comes off to the right here, which is where shaping meets assembly, and then goes from assembly to matte paint here. And so that's the series of points that we now need to figure out. And so one of the things we were interested in doing is being able to create a trace that just shows that feasible region only. And so to do that, we would need to find, for instance, this intersection. And so that intersection we said was where the shaping and the assembly departments met. And so if I come back first to here, the shaping was 13 hours in capacity, the assembly was 18. So I believe this was shaping, this was assembly. I basically need to think of those two as lines now and see where they intersect. So what that basically boils down to is solving the system of linear equations where this is one equation for shaping, and then we also have the equation for the assembly. So I need to solve this 2x2 system of equations. There's a lot of ways and methods by which you do that. I'm going to use NumPy in this case. So if I hop back over into my Jupyter notebook here, I'll just put a note here. I'm trying to calculate the intersection of the shaping and assembly department constraints. And to do that, I'm going to define a NumPy array that I'll call A. And it'll be a two-dimensional array where I'll grab the coefficients of my equation here, 1.25 or equations 1.25 over 3600 will be my first entry, 8.75 over 3600 will be my second entry. And that's the first row of this 2 by 2 matrix that I'm creating. And then the second one would be 8 over 3600 and 10 over 3600. I'll create another, will end up being a column vector here with 13 and 18 is what I'm thinking of it as. And then I should be able to solve this using a portion of the NumPy package. And I'll just call this intersect shape assembly. I could do NumPy's linear algebra module, if you will, dot solve. And print it out. And so it appears the intersection here between those two is this values here, this ordered pair 1721.7 roughly and 5102.6. So that allows us to know that point. The next point would be right here, and we know that map paint is at 4800, so that gives us the X part of it. Then we just need to figure out where that meets on the assembly line. So let's just make another note here just so we keep things straight. I'm now looking for this intersection of mat paint and assembly constraints. Make sure that's in Markdown. And so again, what I'm thinking of here is I know the assembly one, the map paint looks like has 4800. So coming back over here to if it green this time. So which one of these is matte paint? Matte paint had 840 pounds. It would be this one. So in this case, I know x sub b is going to be equal to the 840 times 16 over 2.8, which from my plot over here, I can see that that's going to equal 4800. You can see that's a straight vertical line there. And what I want to do is now look at my assembly and be able to substitute this value of 4800 for the x sub b here and solve for what the corresponding x sub d would be. So I guess we'll say 8 over 3600 times my 4800 plus 10 over 3600 times x sub d is equal to 18, and I want to solve this for x sub d. I guess for that, do a little bit of scratch work here. There we go, so we can all see. I know mat x sub e is equal to 4800, and so x sub d then would equal what? In this case we'll say assembly x sub d is going to equal 18 minus 8 divided by 3600 times 4800, or mat x underscore e, and then all this times 3600 over 10. Looks like roughly 2640. Let's see if that makes sense on the graph. Yeah, 2624 roughly. There, yeah, it looks like right around 2640-ish is what I'm seeing here, so I'm fairly confident we're in good shape there. Alright, so now we've basically figured out what the points are going to be on our feasible region. So with that, let's go ahead and actually create a trace associated with it. And so what I'm going to do is create another trace here, go.scatter, and I will have a set of x values and a set of y values here. And I'll say the name is the feasible region. And let's just start at the origin and work our way in a, say, clockwise fashion around it. So the first point would be 0, 0. So 0, 0. The second point will go vertically, so that'll have a x coordinate of 0, and the y coordinate would be wherever this shaping constraint hits the origin, and it looks like it hits right there. I'm going to truncate that a little bit. I'll say 5,348.6. 5348.6. And so at this point we've hit that. Now we need to find this intersection here. This is where the shaping and the assembly constraints met, and so we know that ordered pair from above. So let's call it 1721.7. And for the vertical, 5102.6. Zooming back out on the plot. Now we need to hit this point here, and that's what we just solved for. And so we know x sub e is 4800, and x sub d is going to be that 2640. The last one now we have is here, and that's 4800 for the x. It's a vertical line, 0 for the y, and I guess not quite the last one. I'm going to go ahead and close this polygon as well, so I'll come back to the origin at 0 and 0. And so with that trace, let's go ahead and create another figure. You reuse that same layout for the most part. And we end up looking with something like this. Let's go ahead and add a fill to that as well, and just say fill equals to self. That should fill it. And I'm also going to adjust the title of that layout. We'll just call it the feasible region. Okay, so it's been a little bit of work, but at this point we have now defined the feasible region for this problem. Every point inside of that blue shaded polygon represents a combination of economy writer pencils and deluxe writer pencils that we now know that will satisfy all the constraints of our model, so that's great. And so the next part will be to start playing with the objective function, because what we can do is take that objective function and actually start plotting different values of the objective function as lines on this chart. And so the way to kind of think about that, I come back over here. I'll just use white now. Is our objective is to maximize 0.41 x sub b plus 0.84 x sub d. And so this is some profit. So I'll say, hey, I've got some profit which is equal to 0.41 x sub b plus 0.84 x sub d. And the thing that I'm going to do is I'm going to find where this line intercepts the two axes. Another way of thinking about that is I've got, again, a Cartesian system that looks like this. I'm going to find an intercept here, and I'm going to find an intercept here, which will allow me to plot the line in between it. So if I let x sub e equal 0, then I can know that I'm going to have the ordered point 0, comma, what, p over 0.84. And similarly, if I let x sub d equals 0. That will get me to the point p over 0.1, 0.41, excuse me, comma 0 there. And then I can then create a trace in my Plotly graphing object using these sets of x and y values. So with that being there, let's come on over here and create a system to create the objective function traces. So I'll say obj traces to be my objective function traces. I'll say for p in some list of profits. At this point I don't really know what the profit's going to be, so I'll just say 1,000, 2,000, 3,000, 4,000, 5,000. And for each one of these I'm going to append a instance of the scatter object, where I'll have a certain x array, a certain y array, or list in this case, and the name will be profit, and I need to be able to differentiate them right, so I'll say profit and put p in here and do a little formatting. So now I can just put in what I have here. So a 0 is going to be related to p divided by 0.41 for the y. So that's this first set of x's. Or no, excuse me. I need to do 84 here. I'm going across. 0 for the x, 0.84 for the y. That's the first point. And then p divided by 0.41 for the x and 0 for the y. Running that gets me a bunch of objective functions traces, and so now let's create another figure that actually shows those with the feasible region. So I'm going to say the data is the feasible region as a list, but then I'm going to also add to it my objective traces. And we will plot this out. And let me change the title real quick. All right, so what we've done at this point is we've gone through and we've created lines now which are associated with discrete values of our objective function. And we've also overlaid that on top of the feasible region. And so if you start looking at this, you'll notice that for a profit, say, of $1,000, that line is totally included inside of our feasible region. So that means that any profit of $1,000, any combination, I should say, of economy writer and deluxe writer pencils that will yield $1,000 is going to be valid and not satisfy any of the constraints. But if I come back up here to the purple line, notice I've increased profit to now $3,000, and as I continue to increase, this line goes farther and farther off and to the right. But at $3,000, there are portions of the combinations that are outside of the feasible region, for instance, points out here, and there are portions inside. So what I interpret that as is yes, I still have possible to obtain a profit of $3,000. I just have to be a little bit careful on what I pick. And so I continue to progress this line over, up and up again until it just barely gets inside of the feasible region. And it looks like that's going to happen at this point right here. Notice this is very close to it. Looks like it's actually off by a little bit there. So it's going to be a little bit less than 5,000 with the values that I've got in my model right now. And so this point right here is going to be the one associated with the feasible solution. The reason I know that is because as I grow this line farther and farther out, at some point it's going to be where it just barely touches that point. Kind of like from just looking at this zoom level, you would see it just barely touches it. And so we would then say that this location is the optimal solution, and in this case the optimal solution is associated with producing roughly 1,721 of the economy bags and roughly 5,102 of the deluxe bags. And then we would say that profit is going to be right around $5,000. If I wanted, I could take the exact values here and plug it into the objective function and get the more precise value there. On both of these cases, I'm off a little bit from the other videos you'll see, partly because I've got some rounding happening here with the objective function. I'm truncating that to 41 and 84 instead of carrying out that to more decimal places. And also, just to make sure we're all understanding, this isn't a coincidence. The fact that the optimal solution is occurring at one of these points on the polygon that I've created with the feasible region is something that was developed by a guy named George Dantzig when he was developing this simplex method. Basically, it's a mathematical certainty that the optimal solution of a linear programming problem is going to occur at one of these extreme points of vertices of the feasible region there. And that's one of the things that's nice about this graphical approach, is it's very easy to see this happening and it becomes a little bit more intuitive. So hopefully this video helps get your mind thinking about linear programming problems and shows you a graphical solution of solving them. And also, I'd encourage you to watch the other videos that I've got on YouTube as well that show how you can actually solve this same problem using software solvers, in this case like MS Excel, as well as Python, having a nice combination of tools using Python, Pyomo, and GLPK.